So in last lecture, let us quickly recall what we did. We derived expressions for the total kinetic energy of a system of particles, where we had a system containing m1 to mn number of particles, and each were having velocity v1, v2, and vn uh, respectively. So, uh, so we derived this equation. Basically, this equation, if we see, this tells us that the kinetic energy of the system of particles is basically equal to the kinetic energy of the center of mass plus the kinetic energy about the center of mass. So if we take our frame and move it with the center of mass, then whatever would be the kinetic energy of the body, that is what we call as the kinetic energy about the center of mass. So this means that even if the body is not moving, there can be kinetic energy due to this. So next we uh, next we saw that if we take the dot product of the net external force with the velocity of the center of mass, it is nothing but the derivative of kinetic energy of the center of mass. So this was another useful expression which we will be using quite often. So then finally we also derived the derivative of the total kinetic energy of the system of particles, and we saw that the first term was same, that is net external force dot with uh, the center of mass velocity, which basically is the translational power by the external forces, and then internal forces were dotted with the individual mass particles velocity, and when summed over all the system, so this is the power by the internal forces. And there was another term which I call that it is something which accounts for the rotational energy of the center of mass, about the center of mass, sorry. So, and we saw this example where the net external force was 0, so this term was 0, and there were no internal force, that is, there were no interaction between M1 and M2, so there was no power by internal forces. But we can see that if this system exists, both M1 and M2 will move, or if they are connected, they will rotate. So they will have obviously the kinetic energy, and that is this term, the third term. Okay, I think we took the example of Lagrangian method, but I think we stopped in between, yeah?
Yes, sir.
Last time. So let us this time continue with the same. So let me take. So before going further, have you any questions?
No, sir.
Yeah?
No, sir. No, sir. Sir, can you, sir, can you little bit explain that if body is not moving, that is the center of mass is not moving, but still the system possesses the kinetic energy that is about the center of mass.
Okay. So let us take an example. So let's take this example. So this is a disk. Okay. And
Yes.
this is some axis. So basically this axis is passing through it. Okay. So and this disk is moving like this. So it is rotating about this axis. So you can obviously see the center of mass of this system is not moving, isn't it?
Yes, sir.
Yet it has energy, kinetic energy. And what is that kinetic
Yes.
energy? That is rotation.
It is rotational kinetic energy.
Yeah, and you might be knowing that rotational kinetic energy associated with it is 1 by 2 I omega square. We will be calculating
Yes,
these things, but for this time, you can remember it. Is it okay?
yes, sir.
Okay, so let us
And,
continue
and
with
sir, this kinetic energy is nothing but about center of mass.
yeah, it is about center. That third term. I think I already told that this is my intuition that it is something about the center of mass, but you need not to look it like this unless and until you utilize the terms correctly, you will get the correct answer. And see, when you will be going higher and higher in dynamics, so you will be dealing with the systems having n number of dimensions. So to visualize things, it is so you should now try to build a habit not to visualize everything. Sometimes going abstract is also a good thing. So in our school days or in our higher secondary level, 10th, 12th, we used to build intuitions. Um, what I can say, like for everything we want some visualization. But
Yes, sir. Yes, sir.
when that creates a problem, that itself creates a problem. I realized it very late. So you like I was thinking when we are dealing with the Newtonian mechanics and we have we have three-dimensional this acceleration. So suddenly we jump to the this Einstein's relativity, and then people find it very difficult to understand. Then I realized that the basic thing that we find it difficult to understand is only because for Newtonian mechanics we have three-dimensional space where we can visualize it. Well, as I in relativity we have four dimensions. That is, we have three spatial dimension and one temporal. That is one time dimension.
Time,
So
time.
since we are
That we cannot
habitual
realize.
of making imagination and visualization, so it becomes difficult. But
Difficult.
I am saying that where you will be dealing with the systems where you have n dimensions, not only four dimensions. So if you are good at utilizing the equation, so it will be better. So not okay, it is good if you have some visualization of the system in 3D, but try to also build a habit of going into the abstract things.
Okay.
Okay, so this was just a comment about it. Okay, so let us go to the Lagrangian method. So let us take our favorite example, that is this So let us take pendulum. If you have any question, you can stop me in between and I will answer. So this is X and this is Y. So this is a hanging pendulum, and let's assume it is making some theta angle, and so we can define the Lagrangian for this. We write this Lagrangian like this, like we write the Laplacian of some function. The same symbol we use for the Lagrangian, or some people just write Lagrangian as L, but I write it like this. So Lagrangian associated with the system is nothing but E kinetic minus E potential energy. So in last lecture, I told that if we have some particle and we are applying some force F. So and in some frame it has some position vector r of t at any time t. So Newtonian mechanics, Newton says that this d2 r upon dt2 is nothing but f upon m. So this is the trajectory, this is the differential equation which governs the trajectory for this mass. So this is like if we follow the Newton's second law, we can get this trajectory. But there is alternate way which we can find out using this Lagrangian method. So basically what the concept is that if we have some mass m, so it goes from this point 1 to point 2. So it will follow some path. We don't know which path it will follow, but there are n number of possible paths it can follow. For example, it can go like this, it can go like this, or it can go like this. So it can take any path from 1 to n. Basically, there is some maybe forces and other stuff acting on this mass m while it goes from 1 to 2. So what Lagrangian method says is that it will go from this first to second in such a way so as to minimize this uh, action.
Energy or
Yeah, no,
energy
no, no, I will not call this as energy. So in general, this is some action, so it will try to minimize this action while going from 1
to
to
two.
2. It will minimize this action. Now, uh, this equation, that is minimization of this action in differential, when we solve this using variational calculus, we get two differential equations corresponding to this minimization problem. So what are those equations? First, so equations are like this: d by dt of del partial L upon partial qi dot minus partial L upon partial q equal to qi. Okay, so this is the governing differential equation correspond. So if you want to minimize this, this is same as to obey this. Okay, these are equivalent to each other. So how we can solve this pendulum system, or we can get the governing differential equations for this hanging pendulum using Lagrangian. So we will do this. So So now we have this. Okay, let me. So we calc calculate the expression for this Lagrangian as E kinetic minus E potential energy. So what is the kinetic energy associated with this mass? So let's assume that at any time t, the position of this mass is x comma y, where obviously this x is function of time and y is also function of time. And this we can represent it as the position vector. So we can basically write the position vector as x of t I plus y of t j. So this is the position vector. Now what is the velocity? The velocity is nothing but the derivative of this r, and that is x dot I plus y dot j. So what is the kinetic energy? If you remember, the kinetic energy of a particle or a point, since this is a point mass, so we know kinetic energy is equal to 1 by 2 v dot v, and which is nothing 1 by 2 x dot, sorry, so x dot I plus y dot j dotted with x dot I plus y dot j, and this is equal to 1 by 2 uh, x dot 1 by 2. So this will be x dot square plus this will be y dot square. Okay. So this is the kinetic energy associated with this mass. So we can write it here. So
Sir,
E.
what about the 1/2 of m? I think you
Oh
use
yeah,
the m.
yeah. So yeah. So there will be mass also. Okay. This is 1 by 2 m. Okay. So this is the kinetic energy. Now let's move to calculate the potential energy. Okay. So uh, potential energy, or I have write it as EP. It is nothing. If we take this line as the baseline, that is the potential energy at x equal to 0 is 0, then we can see the potential energy for this mass is nothing but minus mg. So potential energy increases in this direction and it decreases in this direction. So it is minus mg, this h. Okay, this h. But this h is nothing but the y coordinate for this mass. So it is minus mgy. So this is the kinetic energy. Sorry, this is the potential energy associated with this mass. So now using this we can calculate L will be equal to. So what is E kinetic? That is 1 by 2 m x dot square plus y dot square minus this, and E potential is minus mgy. So this will be equal to minus 1 by 2 m x dot square plus 1 by 2 m y dot square plus m gy. Okay, so we have got uh, the L. So let's calculate now the governing differential equation, and that is nothing but d by dt of delta L upon delta Q. So here, what are the independent variables? These are x and y. So
X and
this
Y.
Q is basically independent variable. So this is delta partial of Lagrangian with respect to partial x dot, okay, minus partial of L upon delta x and equal to, so what is this Q? Basically, this is some non-conservative force. So you know this gravitational force is a conservative force. So if you go along a closed loop, the work done by the gravitational force will be zero. So there is no non-conservative force here. Okay, so this will be equal to zero, and this will be the first governing equation. The second will be d by dt of, so what will be the second one?
Del
Yeah,
Z upon del Y naught.
not this is not z, this is L, or you can
Wait,
call it r.
master
Lagrangian upon delta
Y naught.
y dot,
Del
so
L
delta
by del
y
is equal to 0.
what is it? Oh, I think I forgot. We have one force which is time, sorry, which is tension here. I forgot, and you also didn't raise any question, which is not a good sign. So basically, if we draw the free body diagram for this mass, so we have mg, which is gravitational force acting downwards, and then there is tension also. So basically, this mg is a this is a conservative force, so we will not take it here, but there is this tension, okay, and we are assuming this theta, so this will also be theta, okay. So in x direction, and this is the x-axis and this is the y-axis. So in x direction, the component of this t will be minus t sine of theta, and in x direction it will be t cos of theta. Is this okay?
Yes, sir.
Okay, so going ahead, we have to use this. Um, Okay, so oh, this equation we require I. Okay, we calculated this Lagrangian. Let me write it again. So what was the Lagrangian equal to? So Lagrangian
One
was
half of m
1/2 of m
x dot square plus
plus
y
1/2 of m y dot square plus mgy. This
mgy.
was our. Okay, now let us solve this first one. So this will be equal to d by dt of. So partial L upon delta x dot. What will be this equal to if we take the derivative with respect to x? So x dot is now the
Dot
variable.
m
X is not the variable. It is the x dot which is variable. We have to take the derivative with respect to x dot.
yes, yes, yes.
What will
M dot
be so this will
m,
be 2 times this
m dot x. Sorry, mx dot
mx dot. Okay. So this will be mx dot
plus 0 0
uh,
0
plus 0 0 0. So I will not write those things. So what will be delta L upon delta X?
0.
So it will be 0
Yes, sir.
and this will be equal to minus t sine of theta. So this is our first equation star. Okay. And what will be this thing? So this will be d by dt of, so partial
My
L
dot
by, this will be
my dot
m y dot. Okay, minus delta L upon delta y will be equal to
0.
uh, not 0, mg,
So the mg sorry.
and this will be equal to t cos of theta. So what will be the d by dt of mx dot?
Where, sir? What,
Derivative
sir?
of mx dot. D by dt of mx dot.
D by dt of mx,
Dot.
so mx dot. It will be, sir, ma. That is our force.
Don't say ma. So say mx double dot.
Sorry, mx double dot.
Mx double dot. Because dot always represents the derivative with respect to time.
Time, yes.
Okay, so mx double dot equal to, no, I will take this in, uh, so
Plus t sine theta.
plus t sine of theta equal to 0. And second one will be my double dot minus t cos of theta equal to mg.
Yes, sir.
So if you remember,
Matrix form.
okay, let you not remember, let we go further and represent it in the matrix form. So we can write it m times 0 times and sine theta times, and we can write this as 0 times m times and minus cos theta times what?
Is equal to 0 m.
X double dot y double dot and t equal to 0 and mg. So is it okay? So
Yes,
basically
sir.
these are the two equations. M times x double dot, 0 times y double dot, t times sine theta equal to 0. This is the first equation. And the second equation is 0 times x double dot, that is 0 m times y double dot minus t cos of theta equal to m. So we have got the same equation. This is the equation which we derived, I think, using dA. Okay, so this is
Yes,
the
sir.
same equation. So what we have got is using alternate way, and the thing here is that it was easier in early days because you have to just deal with the scalars only, kinetic energy and potential energy. But you will see that when you solve the systems using Lagrangian, so even though it is easy, but the thing has become very complex in terms of the number of the terms you have to solve. So when you go back, you will, I think, I want you to do it, but let me see if I can do it in the next class. But you can also give a try. You try to solve the second double leaf pendulum. That is, I will show you what you have to solve. So basically, you will have a system like this. Let's take this as y-axis, this as x-axis. Uh, but let me change so that you follow some standard. Okay, let me change. So even though you will be always seeing some pendulum in a vertical position, but in MATLAB you don't have x-axis like this. Uh, you have x-axis like this, and you have y-axis like this in MATLAB. I am saying. So, but previously when you are dealing with the pendulum and you are choosing this x and you are choosing this y, so a little bit. Inconvenience is created due to the MATLAB convention. That is, this is the x-axis and this is the y. So I want some coherence between the MATLAB axis and what we are choosing. So let you choose a pendulum which is hinged at this point, and this pendulum has two links. So first try to solve this same one link pendulum. So we have mass here, and mg will be acting downwards, and let this be the theta. So try to solve this. This is just I have changed the coordinate system. I am taking y-axis as the vertically upward. In previous it was vertical. So try to solve this thing and see how is there any change in this equation? Is there any sign change or others? Once you solve this one, then you can go for this one. So this is x-axis, this is y-axis, and this is two link pendulum. Okay, so there is a hinge 1, there is a hinge 2, and there is this mass. Okay, so you can use this as theta 1. You can use this as theta 2. So try to find out the equations using the Lagrangian. Try to find out the equations using the DAE method also. Okay, I hope if you understood it for the first single link, you can do it for the double link. But anyway, I might be doing this in the next lecture. So let's take one more example, because this Lagrangian might be new for you, so that you get used to it, how things are working. Like you are very familiar with the Newtonian things, but not with the Lagrangian one. So let's go and solve one more example. Okay. Am I audible?
Yes, sir. Yes, sir.
Okay, so let us take this spring mass system. And let's take this f of t. Okay. So if you go for the Newtonian mechanics, you can directly say that mass times the uh, acceleration of this mass is nothing but
Equal.
the net external force, that is F of t. It displays x units from the mean position. So there will be a recovering force or the restoring force kx if the spring constant is k. So minus kx. So this is the uh, Newton's law, which tells you how the motion is being governed. Okay, so we can write this as if, yes, since this is a one-dimensional case, so we can write it as mx double dot. We take this on this side, so it becomes plus kx, and this becomes equal to f of t. So this is the uh, uh, equation of motion for this spring mass system. So let's go and solve this using the Lagrangian, and let's see if we can get this same equation or not. So now Lagrangian we know is nothing but kinetic energy minus potential energy. So what is the kinetic energy for this mass? For example, at any time it will have some x position and it will have some x dot velocity. So Lagrangian kinetic energy will be equal to, yeah,
One. Yes, sir.
half of mx dot square,
M L dot square. Yes, sir.
and the potential energy,
M. Yeah, sorry, sir. mgx.
there is no gravity. This is a spring mass system.
Sorry. One half of uh, kx, sir. Yes, sir.
Kx
Yes, sir.
square.
Yes, kx square.
Okay.
Sorry.
Okay, so this is the kinetic energy and this is the potential energy for this. Okay. So what will be the equation of the system? So it will be d by dt of delta L upon delta x dot minus delta L upon delta x equal to the external force, that is f of t. So
Sir, sir, sir,
yeah,
it is not. Sir, what you are writing is not visible, sir.
it is not visible. Why?
Code is visible, but what you are writing, the cursor is not moving.
So I mean, what you are not able to see?
It is only showing that the spring and the mass and f of t, and the right side ma is equal to f of t.
Only this thing. So
Yes,
this
sir.
Lagrangian equal to kinetic energy minus potential and nothing like that.
No, 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 sir. I think, sir, you were just uh, telling me that
Okay,
this is.
okay. Let me uh, connect this. I think I should reconnect it, and then we will see. Okay, let me do one thing. Let me close this. Is this visible? This lecture note?
No, sir. It is
Hello?
the whiteboard and the spring mass and ma is equal to f of t. Nothing else.
Okay. Can you disconnect and then you can reconnect? I think maybe there is
Okay.
problem on your side. So is the screen now visible?
Yes, sir. Screen is visible now.
Okay. Now is this visible?
Yes, sir.
Okay, I think there sometimes it happens with the system. I will go to whiteboard. I think it has not stood. Okay, let's rewrite and see. Uh, so is now this board visible? I have drawn a.
Yes, sir. Yes, sir. No, it is spring.
Okay, just wait a minute. So. So I was saying why this I'm using the old one, but yeah, so this is a spring, and this is mass connected. K was the spring constant, and let's assume that it has been displaced x from the mean position, this mass. Okay, so from Newton's laws, this is F of t, which is being applied, and this is the external force being applied on this mass, and there is this kx acting on this side, and let's assume that this is moving with some acceleration x double dot. So Newton says that mx double dot is equal to net external force, which is f of t minus kx, or we can write it as mx dot double dot plus kx equal to f of t. So I was saying that this is the governing differential equation for this spring mass system. So let's go and use the Lagrangian to see whether we can get the same equation or not. So Lagrangian is equal to kinetic energy minus potential energy, and the kinetic energy is nothing but 1 by 2 mx dot square, and the potential energy was equal to 1 by 2 mx. Is it visible?
Yes, sir.
These equations are visible?
Yes, sir. Sir. Current energy and potential energy, sir.
Okay, so therefore Lagrangian will be equal to 1 by 2 mx dot square minus 1 by 2 mx square. So the differential equation will be equal to d by t of partial L by partial x dot minus delta L upon equal to what is the external force, that is f of t. So d by dt of so partial L by partial x dot. So take the derivative with respect to the x dot as variable. So this is 2 times this,
And
2
total.
and 2 will cancel. So this is mx dot minus, take the derivative of this thing with respect to x. There is no
MX.
x, so 0. So 2 and 2 will cancel. So this is mx. I hope this is not m, this is k. The potential energy
Yes,
associated
yes.
with the spring is 1 by 2 kx square, not m. Okay,
Yes,
equal
sir. Yes,
to
sir.
f of t. So what is this? This is nothing but mx double dot and minus kx equal to f of t. So
Sir, can we put the value of f of t?
yeah.
Can we put the value of f of t in this equation? That is mx naught.
Just wait a minute. So basically, I am getting this negative sign here.
It
So
should be
can you
positive.
point out where the problem is? What I have done wrong in this? Because I should get the same equation. Okay. So I have got this and I have got this. So here it is plus and here it is minus. So where I have made the mistake?
Potential energy is negative, sir. I think
Potential energy is negative. Uh,
one half of kx square uh, is yes, sir, it is a negative in direction.
okay, so do you mean that it is something bounding? Yeah, in that case, it should be negative.
If the spring was compressed in nature, then I think it should be positive. And if
No,
you
no,
cannot,
no, not because uh not because of that. Uh, just wait a minute. Give, give some thought and uh, oh. Oh, we have missed one thing. So it is not basically, it is positive. So potential energy associated with the spring is 1 by 2 kx square. It is positive. But the thing where we have made mistake is this. So delta L upon delta x is not kx, it is minus kx. Okay.
how, sir?
Take the derivative of this thing with respect to x, what it will be.
Oh, yes, yes.
Here it is minus. So that is minus kx and there is minus by itself in the formula. So this became, so we get the same equation of the motion as we got from the using the Newtonian thing. Okay. So good. So I think now you have got some intuition regarding the Lagrangian, how we can use the Lagrangian. So what basically are the independent variables? Okay. So go and see if you can solve this double pendulum. So I will give a hint which might be helpful for you. So you can also take this as theta 1 and it doesn't matter. Okay, you can take this as theta 1 and theta 2. So there is a mass here, but before going to that thing, I think you should what should we do? Okay, let's postpone it because I think first we should go for the rotation thing and only then I can uh, we can go for this double link pendulum. Okay, so just hold it on till we complete the rotation. Okay, so now the basic thing is 2D rotation of rigid body. Okay, so whenever rotation comes to your mind, so immediately some body comes to your mind, and that body is something spinning. Okay, so this rotation is always associated with a rigid body, a rigid extended body. You cannot define a rotation of some point mass. There is no rotation associated with the point mass. The rotation always comes with the rigid body or extended body. In general, I should say extended body. So this is the first and the starting point for this discussion. And when people try to, so this is the hardest part in the in this mechanics. People do find rotation stuff as the toughest part in the mechanics. So if you build this rotation concept in a good and precise way, I think you will be enjoying this rotation and other stuff. So this is not the case that even you can see people with big figures, but they are not comfortable with the rotation stuff. So I hope you follow with me, and if you find any difficulty, you ask question. So let's get started with the rotation of the rigid body. So uh, okay, so we have some rigid body, and this is some frame I J, and there is some rigid body. And let's take 2 points P1 and P2, uh, and let's take P3. So we have 3 points P1, P2, and P3. Okay, so there will be a position vector associated with this point 1. Likewise, we have done it for the point particles or the point masses. So there will be R1 position vector. Similarly, there will be R2 position vector. Similarly, there will be R3 position vector. Okay, so if this is R2 and this is R1, so this will be equal to R21. That is position of, sorry, this is 3. So this is position vector of 3 with respect to 1. Similarly, this is nothing but position vector of 2 with respect to 1. And this is position vector of 3 with respect to 2. So we have 3. So let me redraw this picture. So we have this picture, and there is P1, and there is P2, and there is P3. Okay, so this is R21, and this is R32, and this is R31. Okay, these are relative position vectors, and these are absolute position vectors. So this is a rigid body. So what is the definition of the rigid body? The definition of the rigid body is that if you take any two points on the rigid body, any 2 points you can, or whichever
So
points you like. If you take any
that
two points, the distance between, yeah,
is constant. Yes, the distance between them is always constant.
yeah. So basically, if you take any 2 points, let's take some I point and let's take some J point. These 2 points are basically on this rigid bodies. Maybe I is here and J is here. Okay, so the distance, so this Rji, this represents this position vector from I to J, and the definition of the rigid body is that mod of this is constant for all uh, I and J. Okay, I not equal to J. So
Okay.
this is the definition of the rigid body. Okay,
Yes, sir.
this is the rigid body. So if there is some motion, there is some rotation and other stuff, but if the body makes sure that Rji, where J can be any point and I can be any point on the rigid body, but the 2 points J and I cannot be same points. If this is constant, I think it can be same also, because if I and J are same points, then this constant will be 0. Okay, I think this is a more general. I should not write this I is not equal to J. Let me relieve this constraint on it. So for all I and J, okay, any point. If I is equal to J, then this constant will be 0. Are you getting what I am trying to say?
Yes, sir. Yes, sir.
Okay. So uh, this is I and this is J, and this is some body, and let's take some line on this body. Can you take some line on a body?
Yes, sir. Why not?
Yeah. So this is some L1 line of the body, and let's take some L2 line, another line on the body. And this is the theta 2 and this is theta 1. Basically, these are the angle made by these lines with the horizontal or the x-axis, and these lines are attached to this rigid body. So let's assume that this body rotates and it translates also. Okay, and this body reaches to this. Okay, so it translates and it rotates. So this is L2 and maybe I'll make it more, bit more. So since L1 and L2 are also attached to it, so L1 have rotated like this, and this is the this was the original L1 and this is the new L1. So that this is the delta theta 1. That is the rotation made by this. And let this be L2 initially, and this is the L2 after rotation, and this is delta theta 2. This was theta 2. Okay, are you getting my point?
Okay, sir.
So when the body rotates, both these lines which are on the rigid body, they also rotate. Okay, and the change in the angle with the reference line, that is the horizontal line, I have taken that as delta theta 2 and delta theta 1. Okay, so for rigid body, this delta theta 2 is equal to delta theta 1, and it will be equal to delta theta 3 equal to delta theta n. So if you take any line, that is n number of lines, all the lines will go through the same amount of angle rotation. Okay, so this is this you can prove using this what I have already this you can do it like this. Okay, so this rotation is same for all the lines. Is it clear? Yeah.
Yes, sir. Yes, sir. Yes.
Okay, now we define, now let's take this, so we can say that if we define by t, so we can say delta, so it takes some time, let us take it takes delta t time. So delta theta 2 upon delta t, delta theta 1 upon delta T equal to delta theta n upon delta t. So all these are equal, isn't it?
Yes, sir.
And let us take this limit delta t tends to 0. So there is d theta 2 upon d theta 1, d theta 1 upon dt 2, and so on d theta n upon dt. And since this is constant for all the lines, so we call
Omega.
this as
Omega.
omega. Okay,
Sir.
we call this as omega. That is the rate of change of the angle of any line. You can take any line on this rigid body. Take the derivative of the angle it makes with the x-axis with respect to the time. That rate you call as omega. And let us define a vector as omega vector, and this omega vector associated with this rigid body. It is nothing but this omega, which is d theta by dt. Okay, so what is this? This is d theta by dt. And now don't tell me that what is this theta. This theta is the angle made by any line on. You can track any line on the rigid body. What it makes with the x-axis. This theta is that angle. Okay, take the rate, and it doesn't matter which line you take because the rate is same for all the lines. And this omega, now I am defining the omega vector as omega times the uh, k cap, where k is something perpendicular to this rotation. So every rotation is going in this 2D plane, that is IZ plane, IJ plane. And I am defining a vector whose magnitude is nothing but the rate of change of the angle, and the direction is along the k. So this is how I define something omega vector, and we call this as angular velocity. Okay. So it is
Okay, sir.
simple till now.
Okay, okay, sir. Yes, sir.
Hmm.
What is K cap?
Everything is good. Yeah.
K, K, K cap?
What?
K cap, sir. K cap. Omega
It is
vector
the
angle.
yeah. It is the unit vector perpendicular to this IJ plane.
IG plane. That is a Z. Okay, sir.
Yeah, it is there. So because I have written at the top that it is a 2D. See, 2D rotation,
Yes, sir.
isn't it? So that is reason. But this will not be the case always. We will have 3D rotation also. But to get started with, I think 2D is good thing to visualize. So you can visualize things. Once you get uh,
Deal of this.
familiar with thing, then you can go for the 3D. And 3D is not something which is quite obvious. You will see it. Okay. So now let us do some further stuff. And now. Uh, so this is basically a rigid body, and uh, this is I, and this is J, and so this is R J with respect to I, and this is R I. It moves and it translates. It moves and it translates. Okay, so it moves and it translates. Initially, this is Rji, this vector. This vector initially it was here. After the body translates, it is now here Rji, and it has changed this much amount. So this is the delta Rji. This is the change in this position vector of j with relative to I is this, and initially it was here when the body has made some rotation. Now it has got changed to this, and there is some change. That how we define the change? First initial vector and the final vector difference. So that is the change. Okay. So we know that what do we know? Okay, we know that d by dt of r I j is d by dt of r I j. This is, we also call it as, this is I, this is j, this is I, this is j. Okay. And by definition, this is nothing but d by dt of rj minus ri, and it is equal to rji dot. Okay.
Yes, sir.
Are you here or you have gone for a tea?
No, no, sir. I'm here, sir.
It doesn't seem like that, but okay, I believe you are there. So delta rij will be equal to, so if this is some delta theta, okay, so basically what this will be equal to. So we want this, what is the change in this thing? So this is nothing but if this delta theta is small, so we know in circle the arc is equal to radius times this theta. So basically the radius is this rji. So this is very important to understand, rji. So mod of this thing is the radius, isn't it?
Yes, sir.
Okay, so this is the radius. So we want to find what is this change. I am saying that
Theta.
if we take this delta theta very small, so this will be equal to this radius times this theta.
Yes, sir.
Okay, this. But this delta ji is not a the scalar quantity, it is a vector quantity. So this is the magnitude. What is the direction? So direction is perpendicular to this rji vector. It will be perpendicular. So when theta becomes small, this becomes tangent, so that it is perpendicular to this rji. And how we can define a vector which is perpendicular to this rji? So this is rji. You have to find out this unit vector. How can you find?
Unit vector, sir.
Yeah, what we don't know. What is that unit vector? So see, we have find the magnitude of this thing, this, but we have to also find the direction, and direction is given by unit vector. That unit vector should be in perpendicular direction to this rji. How we
Yes, sir.
will get that vector? So we know to find a vector which is
Dot
perpendicular to,
product.
not dot product, cross product. Cross product gives us a vector perpendicular to some given vector. So we have this rji. If we take cross product, but what should we take the cross product with? I mean, there should be some another vector which will give us
Yes.
this vector, this vector which is perpendicular. So we can take a vector out of this plane, that is k vector. If we take the cross product of this and k vector which is perpendicular to the plane, so this vector cross with k, so k cross rji will point in this direction. Are you
Yeah, yeah. Yes, sir. Yes, sir. Yes, sir.
visualizing this thing?
Yeah, yes, sir. Yes, sir.
See, this
Yes.
this is rj and k is coming out. So when you take k cross rj, it will give you this direction. Yeah.
Yes. Yes, sir. Yes, sir.
So I
And
will write here.
all yes, these all three are mutually perpendicular to each other, sir.
Yeah. So basic, but we want this direction, unit vector along this direction. So we can get this by K cross R J I unit vector. Huh? We need only unit vector. We because we have find the magnitude. Okay. So we cross product this K with this unit vector, which is along this. And I have denoted it as RGI unit vector. That is the unit vector pointing in this RGI direction. Okay, so this is equal to Rij. So magnitude of vector times unit vector that gives us vector itself.
Vector
So this
itself.
is Rji and this is delta theta k. Okay. Now taking divide both sides by delta t because this takes some time and take delta t tending to 0. Okay,
Yes, sir. Omega.
tending to. So this will be d by dt of
R I J.
r j I.
R I.
This is
R I. Sorry, RGI. Sorry, sir.
r j I. This is r j I. I don't know why I am writing r. This is r j I equal to. This is d by dt of uh,
Theta
d
R.
by dt of what? D theta. Okay. K, sorry. Yeah, yeah. K cross R J I. Am I right?
Wait, sir. Del Q.
There is only delta theta. So d by dt of this delta, this will become this d by dt of d theta, isn't it?
Yes, sir. Ah, yes,
This
yes.
is the definition of the derivative. I have not done anything uh, great. Okay. So d by dt of Rji is equal to. What is the d by dt of theta? This is omega. Huh? We have
Omega.
defined it is previously. D by dt of theta is omega and k cross Rji. So what is this omega k? We have defined it as omega vector cross Rji. So this is Rji dot. This is a very important equation. So basically what this equation is saying that if you have a rigid body, then the derivative of the relative position of any point with respect to some another point is nothing but omega, that is the angular velocity of that body relative to the frame
Yes.
cross that
Mm.
position vector. Okay, so this is very important. So keep this in mind when we go ahead, we will be utilizing this equation. Okay, and
This is
you can also,
this is this looks like that V is equal to omega R
yeah,
in
yeah,
matlab,
but this is a very general equation. This, so we can write this as, let me comment first, let me write this equation. I will go and comment about what you are. Y J
I
I
omega.
equal to omega cross R J I. So you are saying that it looks like V is equal to omega R, but let me tell you that
It not look
this
like
is
draw.
this looks like it, but it
Looks
is a very general thing because this is for rigid body, and this when you solve it is you solve this for a mass which is moving. This
The point.
mass is a point object. So there is no rotation associated with it. There is no omega. This is a I can give you this as your homework. Then why we are using this equation? See, this equation has come for the rigid body.
Yes, sir.
And this equation V equal to omega r, this comes for this point mass.
Mass.
So what is wrong with it or what is true with it? So this I hope you will think over and come with some good explanation in the next lecture. Okay. So remember, while applying this thing, you have to keep in mind that this is only applicable for the rigid body. You cannot apply this for any body. If the body is not rigid, then you cannot utilize this thing. Okay, because this omega thing is only defined for the rigid body. You cannot
Yes,
define
sir.
for this for non-rigid bodies. Okay, are you getting me?
Yes, sir. Yes, sir. Now, question is why we are using this for the point mass?
Yeah. Now the question is, see, m is a point mass, isn't it?
Yes, sir.
There is no omega associated with this mass. But from your 10th, 12th, and other stuff, always you are saying that omega is the angular velocity of this mass, and you are
Yes.
never questioned him if this mass is a point mass, what do we mean by the angular velocity? So these things I think you should think over. Okay, if something is a point mass, how you can define the angular velocity? I mean, about what point it will be rotating, and think you have to now you should be able to differentiate between circular motion and the angular motion. Okay, these are some things you should look at. I will not answer these questions, the reason being that then you will not appreciate the things. So go back to your home and think over these things before I will answer.
Yes.
Okay. Okay,
Sir,
so
sir, you mean that the omega is not associated with the point mass?
I think I am saying this for the whole lecture. I think
Yeah, yeah, yes, 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 sir.
I mean
I
it,
am just internalized.
and
Yes, sir.
I am emphasizing on this point that omega is something which is associated with the rigid body, with the extended body. There is no rotation associated with the point mass or the point. You cannot define any rotation with the point. Okay, so bear this in mind. And but only thing is that I want you to think why the equation comes right, but why we are using it. Okay, so getting something right doesn't mean that you have done the right thing. Sometimes you do some wrong stuff and you get right answer. Okay, I have given example of this kind while we were discussing that uh, what talk and other things. Okay.
Okay, sir.
Okay, so the last stuff which I want to discuss is I think it will take 10-15 minutes and then we will be over. Okay, so the last stuff is angular momentum and linear momentum of a rigid body. Okay, so for linear momentum, we for this n number of particles, we have already seen that linear momentum is nothing but MIVI, isn't it? Yeah.
Yes, sir.
And also it was equal to M total into VG. So it is same for the rigid body also. You cannot get any simpler version of this, isn't it? You have to take total mass of the rigid body and you have to find the
Mass of the
center of mass
rock.
velocity. You will get the linear momentum. This is so easy. And the rate of change of the linear momentum was equal to m total times acceleration of the center of mass. So this is also something, and this uh, g point, this will be fixed on this rigid body.
Frame.
Okay.
Yes, sir. Yes, sir.
When I say it
Great.
will be fixed on rigid body, it doesn't mean that it is physically attached to that body. For example, let us take this example. Let's
It is
take this.
it, it is fixed in the position of that G is constant with respect to frame. I think so, sir.
Yeah, let us do this thing. So this is some frame. Okay, this
Yes,
is
sir.
some body. This is some body. So I hope you can also guess that center of mass is somewhere here,
Okay, yes.
which is not inside the body. This is simple. Or the simpler thing is you take a ring, the center of mass lies inside this. Okay, not on the body itself. So, but it is fixed. It is fixed related to that body. Okay,
Yes,
it
sir.
doesn't change. Related to that body, this point doesn't change. This is what I mean by fixed. Okay, so now the linear part is easy, but let's go to the angular part. I'm not saying it is difficult, but yeah, you have to pay some attention. So angular momentum. Okay. So we already saw that angular momentum with respect to some C point is equal to C. We are building these equations. We are building these analytical equations, and you will appreciate these things only when we will simulate the things. Okay, so simulation is very important in this course. So already we have seen that if we want to take the angular momentum, if we want to calculate the angular momentum of some body about some point C, this is equal to angular momentum of the body, angular momentum of the center of mass about that C point, plus the angular momentum about the center of mass. Okay, and further we saw that this is equal to Ri G cross the so this is equal to R G with respect to C cross M total VG. Plus what is this? This is summation of RIG cross MIVI. Is it correct? We have done this before.
Yes, sir.
Yeah. This
Yes,
is
sir. Yes.
this is the see position vector of center of mass times the velocity linear momentum, that is R cross L, which uses the angle. This is, and this is the angular momentum about the center of mass. Okay, so now what is this? We can write this as RG. This I can write as same. Okay, and plus this term I can write as summation of RIG cross MI. Can you remember? See, there is some rigid. I am doing this for rigid body. Don't forget that I am doing this for rigid body. Okay. And for rigid body, if we have some I and J, we have just calculated that RJI is nothing but
Minus R
RJI. Sorry. Uh,
omega cross R G I. Minus times
so
R I minus omega.
so this is equal to
Omega cross.
omega cross RJI. I. So we have calculated. Similarly, this VIG, G is some point associated with this body, which I have told you that it is fixed. And there is some VI, there is some point on this rigid body. So we can use this formula for it. So VI with respect to G is equal to omega cross R I with respect to G. Is it correct? Got it?
Got it, sir. Yes, sir.
Okay. So this term I am still writing as it is, that is RGC cross M total VG plus this term I will write as C. This MI I will write it here, and this is RI with respect to G cross omega cross this. See, this is a triple. See this double cross product. Okay, this vector crossed with this vector. So we have a formula for this, and I will show you a formula where you can remember this forever. I hope if you have little intelligence, doesn't need something big. If you have A cross B cross C, okay.
Yes, sir.
It is nothing but this.
A dot B.
If you wake up tomorrow, do you think you will remember this formula?
No, sir.
Yeah, this is good. So, what is the way to remember it forever? Is
Start from B.
this. No, I will show you how you can remember this. This is back and this is what is what happened? Wait, what is going on? I don't know what is going on. Let me do this thing. What is happening? I didn't do anything, and this is doing this thing.
Back and cap.
So back, what is going on? I think I need to.
It is AI.
Uh,
AI, artificial intelligence.
so this is. Yeah, what is happening? I cannot just understand. I think something is wrong. Okay, let me keep it aside. So I will use cursor. So uh, now I am not even able. Yeah. So this is back cap. Okay. So what is A cross B cross C? It is back cap. And you have to just remember that the first one is the vector. Okay, that is B is vector and C is vector. And the last two you have to dot product. This is what you have to remember.
Yes.
Okay.
Sir, it is a B cross A dot C.
No. This is B times. This is a scalar. You are multiplying some vector with a scalar.
Oh yes, yes.
This is a scalar multiplication. Okay. That is why I am saying that you have to remember that the vector here is only B. The vector here is only C. And you are taking the dot product of A and C. You will get some scalar. You multiply it with this vector so that it changed its magnitude. Okay.
Yeah,
So back cap, you have to remember this formula. Now we will be applying this formula here to see what magic we can get out of this. Uh, so applying this same, what we will get? This first term is same. I am not writing this. This second term will be M I. See, this is A, this is B, and this is C. So we first term will be back. That is omega cap. Back A. What is A? Ri. Okay.
Yes, sir.
Ri with respect to G
G.
dot. What is C? Ri
G.
with respect to G. Okay.
Yes, sir. Minus.
Minus C. What is C?
C is
Ri.
R I G.
Rig. Okay. And what is A? It
R
is
I G.
Ri
G cross omega. Dot omega.
dot omega. Okay. Dot omega. Uh, okay. So this will be equal to summation of mi omega. What is this Ri dot Ri?
R I G square.
Obviously. Uh,
R I G
what
square.
is what has happened with this pen? Boy.
But it is okay. It will not disturb.
Huh?
It
I
is,
am
it is
not
okay.
even touching it on the pad. I am not touching it. From distance, it is doing this thing.
Previously, it was also, sir, done
Yeah?
before 1 month before. This was also happening on your whiteboard.
Oh, now it has started working. Okay. So we know that if we have two vectors, v dot v is nothing but mod of v square, isn't
Square.
it? So
Yes, sir.
this is mod of rig square, and this is minus. What is this thing?
R I G
Dot it with
dot V.
omega.
Wait a second. That is zero.
Yeah, because
Become perpendicular each other.
these are perpendicular to each other, so this will be equal to 0. So we are left with h h. We are left with h with respect to c is nothing but r g c cross m total vg plus. So this is first term, and the second term, from second term we get summation mi omega rig square. Okay, so the second term is mi omega rig square. Okay,
Yes, sir.
so I think you are remembering this equation, and you were trying to uh, calculate the angular momentum of some mass. You calculate the angular momentum of that thing with respect center of mass with respect to something, and then you are calculating the angular momentum with respect to the center of mass. This is what this equation also shows,
Sure.
and yeah. So and and this thing is a constant for this Uh,
System.
so what is constant here in this summation? Can you figure out?
Summation of mi and omega, sir.
Omega is constant. So omega is same for all the particles. So this omega we can take out of the summation, isn't it?
Yes, sir. Yes.
So we can write this h with respect to c is this first term, okay, plus
Yes, sir. Yes, sir. And summation of mi rij whole square is nothing but it is the rigm total. RGM
mi.
total.
What is this?
RGM total. Center of no. That is summation of MIRI. Am I correct, sir?
So
Is
summation of mi with respect to g square, this is something which is constant and this is known as the moment of inertia.
I omega, yes, I.
Yeah, this is known as the moment of inertia. Okay.
Mm.
So now we have finally got the equation. We have finally got the equation. What is the equation? That h with respect to c is equal to uh, r g with respect to c cross m total vg plus what was the second term? I omega. Okay, but don't forget that this is only
Rigid body.
for rigid body. Okay, this is very fine equation and very important equation. We will be utilizing this thing. So we have got this we have got expression for the what I can say for the angular momentum of a rigid body about some point C. You can take any point C, but this point should be a good point, and I have already discussed what the good points mean.
Yes.
Okay, so this should be among the good points, and from this we can show, and this is also something you can work out that hc dot, that is the rate of the change of the angular momentum, is equal to mc external. We know because we will see why I am taking the derivative, because we will be knowing the external moments on the body. That is why we take the derivative, so that we can equate something with that external moment. And if we take the derivative of this thing, we will get rgc cross m total and acceleration of this center of mass plus I, and this is about center of mass, and don't forget this. And this, what is this omega? Omega is nothing but omega times k. What will be omega dot? It will be omega dot times k. So omega dot times k. This is for 2D. Huh? Actually, these equations are in general true. These are not. And you can write this equation I times omega, and you can write this equation RGC times m total AG plus I. Uh, uh,
Sir,
uh,
how omega vector is equal to omega dot k?
I am saying omega is omega times k, and omega dot is
Is
omega
omega
dot.
dot k? Okay, yes, sir.
This is vector. Its magnitude is omega dot, and its direction is same as k. It is not changing. Unit vector is not changing. Only the rate is changing, isn't it?
Okay, got it.
So what I said is that these equations are in general true for 3D. But the thing is that we have to look at this IG term. So this IG term here, it will be some scalar, but in 3D, it will not be a scalar, it will be a tensor. So once we go to the 3D, you will see that how this I changes. So I want you to get familiar with this 2D thing, okay? Yeah.
Yes.
You work out these formulas and try to understand what the angular velocity of a rigid body is, and what are the equations for the how these equations become simple for the rigid body. You do this thing, and then in the next class, I think I will work out some problems related to two-dimensional thing, because now we have some tools which we have generated, and I don't want uh, I don't want to generate some tool and then don't use it. Okay, we have generated 2D tools, so we will be utilizing these things in order to solve some problem like double link problem, triple link problem, and uh, and also in the next class I will be discussing some non-holonomic constraint problems. We have discussed some constraint problems, but now we will discuss some non-constraint problems, and you will see what is the difference between the two constraint problems. Okay, and once we are done with this, then we will go and do some 3D stuff, and that will be the end of the course. So, is there any question?
No, sir.
No question? Why? Why is there no question?
So I will first I will revise this, and then question will be raised, sir.
From previous lectures, is there any question?
I have not completed revised previous lecture, sir, due to some.
Okay, but there should be no like
Argument.
excuse for these things. You should always delay other things over your uh, what I can say. So have I stopped the recording?
No, sir. No, sir. I think no.
Not yet.